This is Juno 6, paper 2. School caretakers often use trucks such as the one shown below to move heavy objects around. The design of the truck makes it easier to lift the load, and the wheels make it easy to move the load from one place to another. On the diagram, mark and label the position of the pivot. Now, the person's going to pull it down and the load's here, so it's going to have moved about the wheel here. So it's the bolt in the centre of the wheel, so we're going to label that P there. You should also mark in the load force and the effort force needed to lift the load. Show clearly where they act and the direction in which they act. Now this is the load, and the load is a box or whatever it is. The centre of gravity of the load is going to be exactly in the middle. And the load is going to act straight down, and straight down is down towards the end of your page, down towards the centre of the earth. Effort force is going to be exerted by the person, and they're going to pull down with their hand, so they're going to pull in this direction. This is a load force, we call it L, and the effort force, we call it E. Now there were 5 marks here. There was 1 mark for the pivot, there was 1 mark for showing the centre of gravity, and 1 mark for showing the direction of the load. And there were 2 marks then for showing the effort and its direction correctly. Now they said in the mark scheme, the effort direction, they would allow anywhere between, they called it 3 o'clock, which is this direction here, and 6 o'clock. So anywhere in that direction you would have got your mark for your effort direction. Explain using the principle of moments why the design of the truck makes it easier to lift the load. So the whole idea is that you have a certain amount of moment to lift the load that you need. That is provided by a smaller effort force because you're a further distance away from the pivot. So this load force is only this distance away from the pivot. This effort force is this distance away from the pivot, so it's longer. So if the effort is applied a further distance from the pivot, then less effort force, I'm going to call it just in case you're mixed up, less effort force is needed to provide the same moment. Now in the mark scheme they said the word moment had to be mentioned, otherwise you wouldn't get any marks for this question, which is a bit mean, but so you're it's very important that you would mention the word moment. So you need the same moment and a further distance. The diagram shows a solid rectangular block. The block is tilted to the position shown. When it is released, will it return to stand upright again, or will it topple over? Explain your answer. Now you have 3 marks here. There's no reason why you can't draw an arrow from your centre of gravity and show your line of action. So your centre of gravity is in the middle of the block, say about there. You just draw a line in that straight down to the bottom of your page, like that. And you can see very obviously that that line is falling outside the base here. In fact, the base in this diagram is that tiny corner. So there's very, very little chance that that line is going to fall within that base. So to get your marks, first of all, 3 marks. Firstly, you say that it's going to topple over. And then you're going to say that the line of action and it falls outside the base. Now in the mark scheme they were quite generous about this, and they said something about the weight falls outside the base. They would have allowed that. They said that the weight acts to the right of the pivot, so that would have got you 2 marks. And they also said that the weight gives a moment. Now this does give a moment. If this is your pivot, then the perpendicular distance of this from your pivot is this distance here, and therefore it is It is given a moment and it's going to pull over in that direction. But it's easier, I think, to say it topples over because the line of action falls outside the base. And if you've drawn an arrow on that diagram, you've really reinforced that you understand what you're talking about. Right, B part 2. This is probably one of the most difficult questions that pupils find, and very few pupils will actually pick up the full marks for this kind of question. It says to find the weight of a metre ruler or metre rule. Susan set up the apparatus shown below. The metre rule is pivoted at the 30 centimetre mark, and a weight of 2.5 newtons is moved along the metre rule until the ruler is balanced. So you can see this weight on the left hand side here, and it's balancing something, and there's no weight shown on the right hand side, but the weight that it's actually balancing is the weight of the ruler itself. If you think about, say, a blanket box, you open up the lid, you're having to use a force to open the lid. What are you using that force against? You're using the force against the weight of the lid. So everything has a weight, and that weight in terms of a metre ruler will act in the centre. So if you estimate about halfway down that ruler, in fact we'll just measure it here. So the weight of the length of that's about 12.5 centimetres. So we need to mark a point roughly about 6.25 centimetres, which is about there. And we're going to straighten that up again. We're going to show that drawn in here. And so now that looks a little bit more like what you're used to, that you have a moment due to this weight on this side and a moment due to this weight on this side. We have to work out the distance from the pivot. So we know that this is a metre ruler. We're told that it's pivoted at the 30 centimetre mark. You know that the weight of a regular object acts in its centre, so this is 50 centimetres down here, from there to there. But that's not the distance we're interested in. We're interested in this distance here. So if this is 30 and this is 50, then this must be 20 centimetres. So now you're ready to do your balancing moments equation. So we'd start off by saying clockwise moments equals anti-clockwise moments. The clockwise moments are actually on this side, so W multiplied by 20 is equal to 2.5 times 18. And so when you do your sum there, you have to multiply 2.5 by 18, which you can do first of all, and then divide it by 20. And the answer that you're given there is 2.25 newtons. And the 2.25 is in there. So there's a lot there involved to get yourself 4 marks. 1 mark here, 2 marks here, and 1 mark there. And that's what will get you your 4 marks.